Okay, welcome to lesson 1 of unit 6. So this is all about radicals and rationals. So you should have had a little intro to this in grade 11. We're going to go a little bit more deeply into radicals and rationals in grade 12. We're going to be looking at graphs. We're going to be talking about domain and range. We're going to be solving equations. So again, bringing everything together. So we've had this brief reprieve from kind of the transformations piece that we talked about like way back in unit 2. That's coming back a little bit, and we'll see kind of how that plays into what we do in this unit. In addition to that, again, grade 11 topics. So we'll take it back to grade 10 to start with and talk about domain and range. So if we look at this first example, we're looking at domain and range. So just a quick reminder, domain is your X or your input values. Your range is your output or your Y values, the vertical values on your graph. So when I look at this first one, it's linear relation, and so it extends forever to the left and to the right. Doesn't matter how slow or how fast it's inclining, it's going to keep going forever, and that's what those arrowheads are intended to tell us. So when we note the domain, we go from negative infinity, again, always listing the minimum first, to the maximum of positive infinity. And if you, again, have had that predisposition to liking set notation, we would list it as X as an element of the reals. For my range, again, it's extending forever upward, very, very slowly, but it is going to continue upward forever. Same thing downward. So my range would be listed very similar to my domain, from negative to positive infinity, or Y is an element of the reals. Example 2. And it's not shown here, but it does exist. We have our quadratic shape or parabola here. In this case, our domain, again, is unrestricted. Forever left and right are going to be options. It's, again, going to like slow down, and I'm not going to be going outward very quickly, but there's no restrictions that say that it has to stop anywhere. So my domain is from negative to positive infinity. Again, X is an element of the reals. But in this case, we do have a limitation to my range. So if I think of range as like a shadow being created on my y-axis by the graph, if I shone a light from any direction, I'd be getting this kind of a shadow from the left and right sides. And I hit a minimum point where I would no longer cast a shadow. And so that's what we're seeing here, is that when we get to this point, there's no longer a shadow. At our vertex, there's a minimum. And so when I go to list my range, I now have that restriction of not going to negative infinity because it doesn't go downward forever. My graph only starts in terms of Y value at 3. But it does extend upward forever, so positive infinity. So again, remembering that square brackets exist. So they restrict the value and are an actual plottable point. Whereas the rounded brackets, we can't actually put a point there. So when we list this as set notation, we would say that Y is an element of the reals, just like before, but we would say Y has to be greater than or equal to 3. So we'd add that little caveat at the end. Again, either notation, I'm not going to be fussy, so you can kind of default to whatever you're more comfortable with. So we're going to switch gears and now look at specifically a radical equation. So if we just do y equals x, when x equals negative 4, y equals negative 4, negative 2, negative 1, etc. When I'm solving for the square root of x, I'm going to plug this value in under the square root. So for this one, I'm taking the square root of negative 4. Now what I'd like you to do is pull out your calculator right now and try that. What happens? You should get some sort of error. Your calculator should throw a fit complaining that this is impossible because you're saying that something multiplied by itself had to give us a negative number. And we all know that a negative times a negative would give us a positive. And a positive times a positive also gives us a positive. So there's no way that this is possible. Two things of the same number cannot give us a negative value as their product, which means that there is no solution here. There will also be no solution here and no solution here because we literally cannot produce negative numbers by multiplying two of the exact same thing together. So we can only really start this function at 0. And the square root of 0 is 0. The square root of 1/9. You could also think of this as the square root of 9, or the square root of 1 over the square root of 9. You're totally allowed to break it apart like that, if that's a helpful way of thinking of it, which would give us 1/3. The square root of 1/4. If we do the same process, square root of 1 is 1, square root of 4 is 2. Square root of 1, we just said, is 1. Square root of 4 is 2, and square root of 9 is 3. So we were very intentional in choosing these values to start with. Okay, and another thing to note is also 2 is not a perfect number, or a perfect square. So if we go to sketch these now, I'm going to do the first one in pink. So we've got, I'm going to choose my scale appropriately. I got to go all the way up to 9 in terms of my x value, so I'm going to go up by 2. Should we label x and y? So I've got my points of -4, -4, -2, -2, -1, -1, 0, and 0. A ninth and a ninth would be pretty close. A quarter and a quarter would also be pretty close. And we get 1, right, it's up by 2, so a ninth and a quarter would be very, very close. So 1 and 1 is there. 4 and 4 is here, and 9 and 9 would be here. And so again, we get that kind of linear relation of y equals x. Just to give me a different color to work with. If we do this one, I can only start at 0 and 0 and go up from there. So I've got a ninth and a third, got a quarter and a half, and then I've got 1 and 1 again, and I've got 4 and 2, and 9 and 3. So what we see happening here we zoom in, is that in between 1 and 0, my radical, and again this is y equals the square root of x, my radical function actually goes above the linear relation, but then afterwards, once it passes that 1 and 1 point, it's below it. So that's just something to kind of bear in mind, that greater than piece versus the less than over here. So if we talked about domain and range for, again, that linear one, it's just going to be -infinity to positive infinity. And that's going to be the same for my range. It extends in all directions forever. Whereas my radical is very restricted. My domain actually has the restriction of it can only start at 0 and proceed into the positive. And as a result, my range is actually also restricted because I can't use values over here. So I have to start at 0 and extend into the positive as well. And that does, again, it doesn't look like it's going up very fast, but it will go forever. And so it will reach big numbers eventually, just not on any graph that we're drawing. In general, a radical function has the form y equals the square root of f of x, where f of x is any function. Okay, so if we're taking the square root of a function, that is considered a radical. And the key thing here, and we see it in our graph and we saw it in our table of values, is that for a radical function with this form, the domain has to be such that its values of x, so that f of x is greater than 0, because again, we can't take the square root of a negative number. If you remember one big idea here, in terms of remembering how to restrict your domain, is that we can't square root a negative. So, when graphing, we need to use the following facts. If 0 and 1 are in the range of f of x, then the y-coordinates corresponding to these values lie on both graphs. They are invariant points. Okay, so 0 and 1, and we saw that up here. Sorry to keep flipping back and forth, but we have very specifically here and here. And we've used this language before of invariant points, where in the linear form, that original function versus the square root of the function, those two didn't change. There we go. Okay, so 0 and 1 in the range of f of x. Then these will be invariant points, where the graph of f of x lies between y equals 1 and the x-axis. The graph of y equals the square root of f of x lies above the graph. And so again, we saw that above. So before we get to y equals 1, the graph of the radical is above the graph of the original function. When y equals f of x lies above y equals 1, the graph of our radical is below the graph of f of x. Finally, where the graph of f of x lies below the x-axis, this cannot exist because we can't take the square root of a negative. So let's try and apply these. We are given the original functions. We are asked to sketch the graph of y equals f of x, or y equals the square root of f of x, and then state the domain and range. So again, invariant points when y equals 0 and 1. So I'm going to start with those 2 points. In between those 2 invariant points, my graph is above the y value. Okay, is above my original function. Maybe that's a better way of wording it. Because it's not necessarily between it and the x-axis, but between y equals 0 and y equals 1. Okay, beyond it, I would expect it to be below. So again, sorry for my squiggliness and using my stylus. That would even be a little too steep. Okay, so then you can look from there and try and do square roots. So like pick out couple other key points. Square root of 4 is 2, and that gives me another point to kind of hang my hat on, and that would be my graph. And it should be still smoother. Something along those lines. Okay, my domain then would be a minimum of negative infinity. So again, this one's pointing to the left, so that's a little bit different. It has a maximum of 8, and that 8 is defined by a point, so we put a square bracket. The range starts again at 0 and can be only positive from there. When we look at this one, again, my invariant points are when y equals 0 and when y equals 1. Between y equals 0 and y equals 1, that's when I'm going to be above. And then from there, it will be below. So if I take the square root of here, that should be 2, because that's 4, square root is 2. And again, I'm square rooting the y values because I'm taking the square root of the output of my original function, because the whole function is under there, not just the x. And there we go. So my domain here will be starting at -5 and going to positive infinity because it's extending to the right. My range would once again start at 0 because we can't have a negative, so take a square root of a negative, and it would extend positively upwards forever, although very slowly. So what happens if I take the square root of quadratics, though? Because that becomes a little bit trickier. Well, here's what happens. I find my invariant points. 0s, 1s. Anytime it's between those two, it's above my original function. So I'm still using the same rules. And anytime it's greater than 1, my graph should be below, my radical graph should be below my original function. So I'm going to look in 1, 2, 3, 4, 6, 7, 8, 9. Square root is 3, so that's going to be my maximum. So that's going to be kind of where it peaks out. Again, bearing in mind that this is an invariant point. And it should be pretty curved as well. It's tricky to make sure that you cross that spot, so it should be pretty wide, like that. Sorry for that sound. It's me rotating my screen so I can draw it better. So one nice thing about paper is it gives you that flexibility. A little bit less awkward than these screens. And again, we still want to maintain that symmetry, so that's what I'm struggling here for. But again, when my y value of my original function is greater than 1, my square root should be lower than it, and between 0 and 1, my new function, my radical function, should be above it. You see the same thing happening here. So again, 0s are invariant points, 1s are invariant points, and then from there, I know that everything below my x-axis isn't actually going to be included. So this is going to be a weird graph. Everything above 1, y equals 1, is going to be below, technically, and this is technically below here, okay? And here is going to be above, something like that. So now I'm going to actually choose a point. So 4 happens here, so it's 2. Give me a target to kind of shoot for outside of my graph. That looked really funny. Erase that. Okay. And so we get this weird 4, 2. So squiggly again. Bear with me. And that would be my general shape of graph. So it would still kind of curve out a little bit more. So again, just trying to make these graphs as symmetrical as possible. There we go. That looks better. Okay, so that outward curve is kind of a little bit different, but still an accurate graph based on what we were given as my original function. And we were also asked to state the domain and range here. So for the first one, my domain's pretty weird because I actually have 2 restricted ends. I start here at -3, but I finish at +3. I can't extend beyond that. My range is also pretty interesting because it starts at 0, which makes sense, it's in dealing with radicals. But because my original function had a maximum, my new function also has a maximum, and that is at +3, because again, the square root of 9 is 3. For this graph, an upward facing parabola that goes below the x-axis, what we see is this kind of 2-parter. So if you're doing interval notation, you're going to have to bear in mind that you're going to have to use that united notation that I believe we've used before, if I recall correctly. So domain-wise, from the left, I can actually go forever. So -infinity is a perfectly acceptable starting point. But as I follow my graph, I reach a maximum here. Now I'm missing a vertical axis. I'm going to put it here for a lack of any other one to work with. So I would say that I kind of reach a maximum domain value of 4. And I have a defined point at 4, so that's great. But it actually picks up again way over here at 8 and extends forever outward to the right. Now, if I just said -infinity to +infinity, that would not be true to my graph because there is a space where I don't have any values. So it's really important to acknowledge the fact that there is a true break in my graph by using this united symbol. When I do the range, though, I don't need to require that united symbol because there is no vertical break. I have a starting point of 0 in both pieces, and they both extend forever upward. And because of that, I can still write my range as 0 to +infinity. So there's some pretty interesting scenarios that we can come up with, and that's why this is a special unit unto itself, is because when we get into radicals and rationals, we're getting some pretty interesting shapes that we've not really come across before. I believe that we've got this last example. If we take the square root of a cubic, we're going to get even more weird stuff going on. But I can still use my same rules. So I'm going to identify my invariant points to start. Anytime I have a 0, those are invariant points. Anytime my graph equals +1, that is an invariant point. I'm roughly estimating because I checked my scale and 1 is halfway. Okay, so don't just assume that it's the first line there. I've seen that happen on provincial exams before. Be very, very careful that you check your scale. Those are my invariant points. I can also identify right off the hop that anything below the x-axis is not going to be included. So I can take out those parts. From here, I have a general sense of what's going on. This is like 2 and a bit-ish. Hard to say, but we can roughly estimate that our maximum is going to still fall in the same value of our domain. It's just over 2, so it would be around here-ish. And again, we're just sketching, so it doesn't have to be perfect. Over here, I can pick like 4 would be 2 and get at least one extra value to sketch from. So then I go back to my rules and I say, okay, well, between 0 and 1 in terms of my original output, I should be above the graph. I am going to be below it here. Okay, so again, below, above. Again, with a pencil, this is much easier than on a computer. In my opinion, anyways, it shows my hand shakiness. Okay, and again, over here, very close to my original graph, but I am actually different. So shaky, sorry about that. There we go. So it's a pretty weird looking new graph. To state the domain of this one, I've got it in multiple pieces. So I go from -4 to -1, and those are defined. But I also pick up again at +2 and go forever upward to the right. If I was doing this in interval or in set notation, I would say x is an element of the reals, like I always do. And then I would say that x is between -4 and -1. And x is greater than or equal to +2. So I'd have to list them as 2 separate pieces again. So neither are particularly efficient in terms of dealing with graphs that start falling apart like this. My range, although I have a local maximum here where it caps out, overall, I do have the possibility to extend upward forever. So I still start at 0, just like before, and I'm still going to go to +infinity. Even though I do have that maximum here. Still going to state that general +infinity piece. I believe that's my last example. Okay, so I'm going to post some homework to go along with this to practice just sketching graphs given functions, but lesson 2, 3, 4 are all looking at graphing for radical and rational functions. So really being comfortable with these rules is going to be your first focus. So again, those rules, and I'll outline them and kind of in our process how we did it. 1 was identify invariant points. Okay. 2 was kind of knocking out any restricted areas. So identify and then 3 is maybe identify some like key points that you might want to use. So maximum, minimum, easily calculated values. Okay, and then finally, we're going to sketch the curve following our other rules. Okay, and this will be kind of your process that you can use for both radical and rational functions. So that's why I'm not being specific in that 0 to 1 being greater than the original function. That's something you're going to have to remember. It's specific to the radicals, but not necessarily for rationals. So again, homework's coming. Let me know if you have questions, and good luck.